Welcome back to this series of videos where we are learning how to use the Flexibility Hub to define a flexibility workflow inside the Scipion. So in previous videos, we have seen how to use cluster space, annotated space, and its different versions to get different conformational states from our estimated landscape. Also, we saw how we can use the information that we have extracted in the form of a flex class inside the Scipion to get either the maps or the particles that are coming from each of the states we have selected. What can we do with all these different maps or with all these different particles? Okay, so let's have a look at it. So here I have the interactive consensus that we saw previously using the CERNIC 3D. So we are recovering CERNIC 3D particles. I did a UMAP and I did a cluster space with 5 items, which is the optimal number of items based on this optimal clustering that we did before. And from here, I have taken all the conformation I have selected in the form of maps and also particles corresponding to selection 4. Let's start with the particles. So particles here that I have extracted, they are a set of particle flex. So they also have all this flexible information from the CERNICs, or if they were coming from CryoDragon, flexible information from CryoDragon. But for example, for a Scipion, they are particles. So in principle, we can use any of the single particle analysis plugins like Relion, CryoSpar, and so on to get refinements. So for example, here, I have taken my particles. I have done kind of a downsampling of them just to make things faster, although this is not needed in principle. And I have used the auto-refine protocol from Relion to get the conformational state coming from particles 4. What's the problem when you are working with this kind of refinements and particles? Then as you can see, the number of particles is very, very, very low. So even if I have done this downsampling, you are seeing that I am not even able to reach Nyquist, which in this case will be around 6.2 angstroms. I am reaching 6.8. So depending on the number of particles you have, depending on your data, refinements could be a good way to get back your states, or it could give you very bad maps. Anyway, if you are getting a reasonable map, is something that you can use, and it's always a good idea, even if you are getting a low resolution map, to do this kind of refinements and compare them with the CryoDragon representation, with the CERNIC representation of the state, just to be sure that we are getting what we expect, as a check that everything is working fine. The other possibility is to use the maps with flexible information, which is these maps I have extracted here, this set of volumes flex, which I can open, and you can see that these are the reference map in the case of the CERNICs with the CERNIC coefficient vector here. And we can use this information to, for example, recover the new states using the CERNIC deformation fields. The way to recover the maps from different programs will change. For example, programs like Scipion or CryoDragon, once you extract the maps coming from the cluster space or the annotated space, these maps saved here, there will be already a new conformations. Let's have a look at an example of this. So I have here the interactive consensus from CryoDragon. I also did a new map in 3D, and I have run, for example, the annotated space, and I have taken 10 states from here. If I compare the CryoDragon and the CERNIC one, you can see that the CERNIC, the map is always the same, but we have this vector of coefficients, which will allow us to recover the new conformational states. But in the case of the maps coming from CryoDragon, maps are different. So actually, if you are coming from Scipion or CryoDragon, these maps already allow you to see all the different conformational states. Okay, so what can we do in the case of the CERNICs? In the case of the CERNICs, once you have extracted your flex maps with these CERNIC coefficients, there is a protocol called apply deformation. In order to find it, you can go to Flexibility Hub, you go to Data Analysis, and you have here a tab called CERNIC 3D. And here you have a protocol called apply deformation field CERNIC 3D. If we open the form, here you can provide a set of CERNIC flex volumes, which are, for example, these maps I have extracted from my cluster space here. And then you have an extra parameter. By default, it's set to no, and this means that you are going to apply the deformation to the reference map, and you are going to get a representation of the conformational state at the level of CryoEM density map. But if you have a structural model, because you have, for example, trace some of your map, or you have a PDB that you have aligned to your molecule using some tools for flexible fitting and so on, you can also put here a PDB that is aligned to the reference map you have used, in the case of the Cernix, and you can apply the formation fees directly to the structural model. And this means that you will get all your structural states, not at the level of cryo-EM densities, but at the level of atoms directly. After running this program, you will get, again, either set of volumes flex or set of atom flex. In this case, here, I have provided a PDB. So what I am getting are the states at the level of a structural model. And again, you can open all these conformations with Chimera, like for example, I have here. So let's restart this protocol and see what are the conformational states at the level of Chimera. Here we have the Chimera window. I have been playing a little bit with the visualization parameters just to visualize everything more easily. And here we have the 5 different states that we obtain from the interactive clustering, but at the level of a structural model, not at the level of cryo-EM density map. This is one of the main strengths of the Cernix algorithm, and is that you can compute the deformation fields on downsample images, on downsample maps, but then you can apply them to the original maps, to structural models. So it's giving you a lot of freedom to explore the different states at different levels. So let's see what happens, for example, with state 1. And here we are seeing a small rotation of the large subunit. We can also see a state 5, which is kind of similar to a state 1. This other state, which is kind of moving a little bit towards us. And this other one, which is a rotation in the opposite direction of the small subunit. So with this one, you can start getting an idea of what is going on with your changes, either with structural models or with cryo-EM maps. Lastly, I would like to talk about a different protocol, which is not really for recovering conformational states, but it's very useful to understand better what is going on with different motions occurring in our conformational landscape, and more specifically, the motions that are giving rise to a specific conformational state. For that, you need to go again to the particles, like for example, these particles corresponding to my selection number 4, and you need to run a protocol that is called motion statistics, that is found again in data analysis, Cernix 3D, motion statistics, Cernix 3D. This protocol here, you need to provide a set of Cernix 3D particles, like the one I have just extracted from my interactive clustering, and I can provide or not an atomic structure. This is optional. If you provide it, you can also visualize these things that we will see with atomic structures. If not, you will be only able to see them using the cryo-EM map. Then you click on execute, and you will get an interactive protocol. I'm going to execute it again. And you will see this window here, which again, you can resize to make it bigger and to see things better. So in this window, what we are seeing to the left is a representation in 3D of the map, which is also representing some motions, the motions going on for this specific state number 4. But here we cannot see many things. So let's have a look at the representation options. First is a slider called opacity, which controls the opacity of the cryo-EM map, which is shown in white. So here in white, we are seeing the cryo-EM map. And these things here, we will see now what are these. You can also decide to see an atomic model instead of seeing the map. You see that the representation is different, and now we will see how to make this representation better. Let's go next to these mask arrows. So actually, what we are seeing here, if we zoom in, are arrows. And these arrows are telling us for each voxel in the map where that voxel is moving. Or in the case of the atomic structure, where each atom in the atomic structure is moving in order to describe this new conformational state. So this is very useful to understand what are the motions giving rise to conformational state 4 or any conformational state that you have in your dataset. In the case of the map, we have so many arrows. So one thing that we can do is to say, okay, let's do a masking. So I can put here a masking number, like for example 5, and click mask arrows. Now you can see that we are getting much fewer arrows. Let's get even fewer number of them. And now we are getting very few arrows. That is probably easier to understand. And then you have the scaling. So you are seeing that some arrows, like these ones here, are very, very, very small, and we cannot really see them. So if we go to the scaling here, and we put a larger number, now our arrows are scaled. So one thing that we can see here is, for example, that this region in the small subunit is trying to go forward, this other region is trying to go up, and so on. So we can analyze very well and understand very well what are the different motions occurring now in our map. We can even see that some regions are moving very, very little. Even after the scaling, these arrows are very, very small. And we can do something similar with the structural model. So if we scale here the arrows, and we add more arrows, say for example, a scaling of 10, now you can see what is going on with every atom in your structural model. So the problem is that this structural model is not complete, because it was not possible to trace the whole model. But if you have a complete model, you will be able to see much better what is going on. So let's again add some masking, some scaling, add some extra masking. Okay, also you can paint or change the color of the arrows. So here, these arrows here are colored according to the mean of the motion, which basically means arrows that are more yellow, it means that they are moving more and they are also bigger. Arrows that are kind of purple, they are on average moving much less and they are also smaller. But you could also paint all these arrows based on the standard deviation, for example. And the idea of this standard deviation is, okay, probably that arrow is not moving much on average. So if I average all the motions that happen on these 4,000 particles, the average is almost 0. But the standard deviation is much bigger, which basically means that even within those 4,000 particles, there are also other states going on, and some voxels are moving to many different directions. And we can see that, for example, some regions here that were moving a lot, they also have a large standard deviation, which is normal because they are moving a lot. But some other regions here that were appearing in a very purple color, now they have kind of more blue color, meaning that on average, they are not moving much, but actually this is because there are many, many states within these particles, and all these states are moving randomly, probably, and when you average them, you are getting almost a 0 motion for that voxel. Great, so at this point, we have seen some of the tools that we offer in the Flexibility Hub to recover states, higher or lower resolution, getting structural models that represent different states, even analyzing in a more deeper way the motions that are driven one state to the other, and so on. So in the next video, we will see another type of reconstruction method, which is called SART, which is kind of special because it's going to use the information that we estimated from the Cernix, from this landscape, but it's not to explore the landscape, but to actually correct for the heterogeneity, trying to get a map that has higher resolution, mostly in the flexible region. And thank you so much for listening.